Hello everyone, this is Tan here. Welcome to my YouTube channel. Today I present a recent paper on optimism in reinforcement learning with generalized linear function approximation. So just so you know, I will present a series of papers I have recently read in my YouTube channel. So the purposes are that first to force myself to understand the paper correctly and succinctly, and second, to force myself to able to present the technical results to general audiences in an intuitive and easy way. And also, it would serve as my personal archive of the technical results, which I will frequently come back to review when I do research on the relevant papers. Okay, so let's get started to the presentation, today's paper. So today I will talk about optimism in reinforcement learning with generalized linear function approximation. This paper recently accepted to ICLEAR 2021, and this is the archive version of this paper. You can take a look at it, and here I just give some very key technical steps how to establish the result in this paper. I won't go into too much details, but you can follow the detail in the original paper here. So motivation for the paper is that optimism is optimism in the face of uncertainty is provenly efficient in linear MTP as proved in the Jijing Code 19 paper. It is quite famous paper. You should check it out if you work on reinforcement learning. So a natural question is that is optimism also provenly efficient in a model based on linear MTP? So this paper provides a positive answer for a generalized linear model, GLM. So main result is that the algorithm obtains a aggregate of the sublinear aggregate of H of square root of D, Q, and T. So T here is the total number of iterations in the algorithm. H, capital H, represents the episode length, the number of steps within one episode. And D is the dimension of the state space. All right, so let's go to the setup of the problem. The setup is that let's say we have a non-featured map. Phi is go from the state action space to the d-dimensional space, right? So we have the non-link function f from real value function. So the classic linear generalized model is basically that you take the dot product between the feature map and some weight theta in the two-dimensional vector, and then you apply a link function over the result of the feature map of the dot product. So just a quick overview of the reinforcement learning MDP. We had a Bellman operator TH, which should map from one function to another, defined by taking the expectation of the reward and the maximum of the Q as H plus 1 and A for all step H within the episode length. All right. So the main assumption in this paper is that the Bellman operator TH for all H transform any upper bound confidence function into a generalized linear function. So what does this mean? So formally, so here we define the G up function class, which is class of all generalized linear function and all possible upper confidence bound, which is defined as in this formula right here in the bottom of this page. So basically you have the generalized linear function plus some like the confidence up all possible upper confidence bound. All right. So algorithm is quite very simple. So as iteration t, we collect one trajectory as ht, aht, or ht, and following the current policy estimate. So the current policy estimate hat pi hat ht is critical with respect to the reverse value estimate q bar ht minus 1 as shown in the first formula. And then we compute the optimistic value estimate. So q bar ht as a equal to the linear function as sa and theta hat ht plus the upper confidence bound, the empirical upper confidence bound. So where here the empirical risk minimizer for the least squared problem of generalized linear model, HAT is solving for the least square problem, minimizing of the least square problem using the data up to time t, and the empirical covariance metric lambda ht is just compute using the data up to time t. So analysis. So at the beginning of time t, time set t, we have data available up to time t. All right. So thus we will analyze the value estimate q bar t minus 1h at the beginning of time step t. So I decompose three-man step to establish an upper bound of the regret in the paper. So it's a quite general steps that the other similar paper should follow the same procedure with different technical details. First is per iteration error. So the error for each time step t, optimism principle, how can you guarantee the optimal optimism principle in the algorithm, and then regret decomposition or error propagation, how you propagate errors across different iterations over time. First is control per iteration estimation error. So prior to each fifth iteration t, we control the error between the theta hat h t minus 1 is base optimal predictor, theta bar h t minus 1, but theta bar t minus 1 is like the weight of the payment operator applied to the q bar h plus 1 t minus 1. All right, so the result is that we can concentrate the error, we can control the error between the value estimate q hat h t minus 1 and q bar and th q bar h plus 1 t minus 1 by the confidence metric, the empirical confidence metric. All right. And the optimism, it will be true that the estimate q bar ht is the optimistic estimate of q star h for all ht. And the idea is that we use the induction step from h equals capital A to A equals 1, and we note that because definition of the estimate q bar HDSA, we can easily prove the induction step. Use the error propagation or decomposition. So this paper proposes a novel way to decompose the error over iterations, which is quite general and no such to any function approximation. And we can say that this error decomposition is one of an important contribution of the current paper. So the result is like this. So we define ft minus 1 be the filtration of the data up to time t, not including t. So assume that there is a random function constant ht minus 1, which is ft minus 1 measurable, such that we can bound the error, bound the Bellman error, the error of the q bar h t minus 1 and th q bar h plus 1 t minus 1 with some error. With this error controlled by the confidence h t minus 1. So with that inequalities, with those inequalities, we then have the following decomposition as shown in the paper. So the nice thing here is that zeta here is a difference martingale sequence adapted to ft minus 1. So which is, because this is martingale, it can be bounded, all right? It can be bounded by Asimov's inequality. And then the sum of the confidence covariance, empirical covariance matrix can also be bounded. So at the result, we can bound up about the regret the optimism algorithm in reinforcement learning based on with the generalized linear function approximation. So that's it for today. Thank you for um, watching my video. So I try to, if you have any like comments and feedback, just leave it below in the video, and I will try to improve my presentation in the future. Thank you.